Yeah. Thank you all for staying so late. I appreciate it. Try to find the clicker next to you because I'm going to have some questions for you. Okay? All right, so today I'm going to talk about compressed sensing in MRI. I have the following conflict of interest. My group received research support from GE Healthcare. Okay, MRI is a great imaging modality, but the data collection is inherently a slow process. And so people try to figure out ways to sample much faster, but ultimately there is a limit. So one of the possible solutions, if the data collection is inherently a limited thing, then to do faster imaging by reducing the data and reconstructing the images based on the fact that the data is redundant, or exploiting various redundancies. So the fact that there is redundancy in the data, that reduces your sampling requirements. So the more you know, the less you need. So this is just a fictional graph that I invented. And what it shows really, the y-axis goes from how many measurements you need, from nothing to everything. And on the bottom, the x-axis shows how much prior knowledge you know, from nothing to everything. And so if you know nothing, then you need to acquire everything. That is determined by the Nyquist criteria. And so if you start knowing something, then you can go below the Nyquist limit. And there's a bunch of methods that allows you to do this. And all of them differ from with the type of prior knowledge that they use. And of course, if you know everything, you reach the Hennig limit, which means that you really don't need to acquire any data at all. And we would like to reach this, but I think we might stop somewhere around here. Okay, so the type of redundancy that I'm going to talk about today is image compression. And so medical images are, in fact, compressible. Yes, they are. And the standard approach is to first collect the data and then compress it. But what we really want to do is this. What if we know that the images are compressible? We know that they're compressible. Why do we need to collect all the data in the first place and then throw most of it away? And so this idea called compressed sensing tries to sense the compressed information directly by making fewer measurements and then reconstructing images based on the fact that we know that these are compressible. And this is due mostly to Emmanuel Candescendone, although there's a lot of practitioners that have been using similar ideas. Of course, it doesn't have to be images. It can be also videos, multidimensional signals, and so on and so forth. Okay, so here's a question. What are the key elements of compressed sensing? A, acceleration, reconstruction, and speed. B, FFT, wavelet transform, and thresholding. C, density, coherency, and linear reconstruction. Or D, sparsity, incoherency, and nonlinear reconstruction. And A, B, C, D correspond to 1, 2, 3, 4. And I'm sure you can deal with that. Okay, so the answer is 4, according to you, sparsity, incoherency, and nonlinear reconstruction. But we'll see at the end because I'm going to repeat the question, and I hope to get a much more fine distribution. Okay, so the purpose of this talk is really to explain what compressed sensing is, and I'm going to put emphasis on intuition rather than on rigor, and if you're interested in equations and proofs and so on and so forth, I do recommend to go through the papers. What I will do, I will start with ideas like denoising of sparse signals. Then I will move into what happens when you subsample and the type of aliasing that you're going to get. And then I'm going to connect the aliasing removal in the reconstruction with denoising. Okay, so this we're going to go through in the next 25 minutes. Okay, but because this is Salt Lake City, and I have to show this beautiful images from the University of Utah, where they use these kind of ideas that I'm going to talk about today in order to get more information. So this is an example of accelerated cine turbospin echo of the neck. And normally you need 2 averages in order to avoid artifacts of motion. But if you actually sort out where the data belongs to over time within the cardiac cycle, and you use these acceleration technique and sparsity and so on and so forth, you see this beautiful dynamic in the neck. It's just amazing to see. All right, so let me first describe a surprising experiment, although it was done almost 10 years ago, so I guess it's not that surprising today. But what they did is they took the Shep-Logan phantom, computed a Fourier transform, and then went ahead and randomly threw away 84% of the samples. And if you try to do a standard reconstruction, like minimizing the norm, zero filling, so on and so forth, you get a corrupted image. But if you do a compressed sensing reconstruction, you can accurately get what you start with, even though you subsample the data significantly. Now, what's the implication is, and what's exciting about this is if you do the same with a brain image, maybe not throw away so many sample, a little bit less, you get a standard reconstruction will give you this kind of incoherent aliasing or incoherent interference. You know, I'm not sure you can see this with the dynamic range of the screen, but a compressed sensing reconstruction will give you something that is clinically viable, very, very close to what you started with. And so because MRI data are obtained in K-space, or in the frequency domain, this is really a potential for significant scan time reduction. Now it's all about really sparsity and compressibility. So let's talk about what sparsity and compressibility are. Okay, sparsity and noise. What is a sparse signal? I would say, if you agree with me, that this is a sparse signal, right? So this looks more like an NMR spectra. And I would say this angiogram is a sparse 2D image. Okay, because most of the coefficients are black and some of them are white. Okay. What is the least sparse signal you can think of? Well, I would say the noise is the least sparse, or globally not sparse, because it has information, it has energy everywhere. What's really powerful about a sparsity model is that when you have a sparse model, a sparse signal is corrupted with noise, it's very, very easy to separate between most of the noise, most of the signal and the noise. And the separation can be done by just a simple thresholding operation. Okay, if I threshold the signal, I separate it between most of the signal and the noise. So this is very, very powerful. I don't need to know where the signal is, but just that there's just few coefficients. And because I set a threshold, I was able to separate. Let me talk a little bit about thresholding. Hard thresholding, just setting a threshold and removing anything below, can be a little bit sensitive, and that can result in large spurious residuals. For example, if you have a noisy signal like this, hard thresholding will give you kind of sparse residual that actually belongs to noise. What instead you can do is use a soft thresholding. So if a hard thresholding goes like this, you know, if you put an X, you get a Y like that, then soft thresholding just, you know, starts at 0 at this point instead of going over here. But that gives you less spurious residual. It does give you a bias. It's a bias estimator. But it turns out it's also equivalent to minimizing an L1 minimization, so solving the closest X to the noisy Y that has also some small L1, which is the sum of the absolute values. And that actually relates later to compressed sensing. But you can see that it's much less sensitive. Okay, but signals don't have to be sparse in the signal itself. Here's a signal which is not sparse, and it can also be noisy. But then that signal has sparse edges, so each pixels are very similar to each other, except on the boundaries. And so you see that here it's very easy now to separate between signal and noise, just because it's sparse. I would say that brains perhaps are not sparse themselves, but they can have a sparse transformation. For example, the wavelet transform is a way to sparsify brain images, for example. And what's a wavelet transform? This is a wavelet transform. This is the magnitude coefficient of wavelet transform of the brain. But these really represent high frequency information. These represent low frequency information. Then you can go and sequentially separate them into low and high again and again and again. But the cool thing now that I've had a sparse representation of this brain image using wavelet transform, I can denoise this, this signal just by mere soft thresholding of the coefficients, like this. And then if I now reconstruct by computing the inverse wavelet transform, I get a denoised representation. And you can appreciate how well it is denoised while preserving a lot of the features. So just by moving into a sparse representation, I was able to separate better from noise and signal, just by a simple thresholding. Now, of course, there can be more sparse transformation, like this cardiac image, for example, a cardiac video. You see how it changes position versus time. It will have a sparse temporal frequency because the signal is quasi-periodic. Okay? What you can do, and then you can use this to denoise this sequence. What you can also do, if you look at the structure of the sparse coefficients, they also have structure, and people have also been using these ideas of group sparsity to get better representation and denoise even further. Now, what's the relationship to compression? Well, because we compute a sparse transformation, we need only to store the non-zero coefficient, and that corresponds to the compression. So the more coefficients I add, for example, in the wavelet domain, then I get a better representation of the object. And so here, up to 5%, I get almost a perfect reconstruction. Okay, so the signal is very, very sparse, and that helps me represent it, but it's also compressible. Now, there's an increasing body of literature of more advanced techniques rather than just pure sparsity using wavelets. For example, if you look at this image over here, one way to do it is to design a dictionary or design a transform that makes it more sparse. And so, for example, this block over here can be represented by just a few coefficients of a dictionary, and that can be used to remove noise. The other approach is block matching 3-dimension, where it uses the image itself as its own dictionary, where you take this block, you find the closest blocks that are the blocks that are closest to it, and then what you do is use these as dictionary elements, and then reduce noise using this. And these are advanced techniques that can also be used. Okay, so here's a question for you. Pick up the clickers. Sparsity model is powerful because A, it's a simple model. B, many signals can be made sparse. C, easy to separate signal from noise. D, all of the above. Okay, so the answer is all of the above. So touche for all those, pick 4. Yes, so it is. So basically, it's a very simple model. You can make a lot of signal sparse, and you can separate signal to noise. Okay, so there's another question. What is likely the most compressible to least compressible ordering of these images? A, this is the DC angio first, most compressible, then cardiac, then brain, or brain first, DC angio, then cardiac. I guess you can read by yourself. This is a little bit harder. And yes, the answer is 1, DC angio, then cardiac, then brain. And the reason is that DC angio is also sparse in the signal itself, but also has a very simple temporal behavior, just signal intensity changes. Whereas cardiac, there's quite a bit of things that are going on. The thing is that images, so why not a brain image, for example? It might be represented by less coefficients, but if you look at the ratio between the number of coefficients that you need to represent and how much coefficients you have, then 2 images are much less compressible than videos. Videos, of course, we can compress much more than images. And of course, images we can compress better than sound, so on and so forth. Okay, so how do we move from sparse signal and sparse signal to noising through sparse sampling? We're going to do it through the Fourier transform. Okay, how do you know this guy's insane? Okay, that could have been a question, but I'll say that the spectrum is imaginary, is not symmetric, so the cat must have an imaginary component. All right? Okay, let's move on. Okay, so if you have a signal and you acquire its Fourier transform, there's a specific rate that you need to measure in order to reconstruct it, and that is given by the Nyquist criteria. And once you have it, you compute an inverse Fourier transform and get the image. If you go to sub-Nyquist rate, for example, uniform subsampling, you would get this coherent folding. Okay, so that somewhat, I think, makes it harder to recover because there's some ambiguity here. Things kind of wrap. If I go further and further, it's just going to get worse and worse. Okay, maybe this is not the right way to go. What I'll do then is, what if I sample randomly? Sample randomly the frequency domain. Well, what I get is this image that is clouded by this kind of non-coherent aliasing artifacts. So it's getting close, but still not it. What if instead I go, let's say, for a variable density random sampling? Okay, so now, look carefully, I've got the image, but now the image is corrupted by this noise-like artifact, noise-like aliasing. Okay? Pay attention. Now, people have realized this, and there's a paper by Scheffler and Hennig back in '98 where they realized that subsampling a radial acquisition gives you these streaking, non-coherent artifacts, but you can still see through those artifacts and see the structure. And Dana Peters back in 2000 had a beautiful paper and she realized that for sparse signals like angiograms, the artifacts are in fact benign. And this idea is really great for angiography. Now, when you look at angios, you often do a maximum intensity projection through the volume. And if you think of what a maximum intensity projection is, it's really some form of a thresholding, which brings us maybe back into the first thing that I described about sparsity, thresholding, and removing noise. So here's a train of thought. I showed you that most signals could have a sparse representation, and once you have a sparse representation, it's easy to separate between signal and noise. Now, when we subsample signals, we get aliasing. But what if we can create that aliasing to look like noise? Maybe then we can use this idea of sparse models or modeling the signals such that we can remove these aliasing or remove the noise using denoising techniques. And this is really the idea behind compressed sensing, is really denoising the artifacts. So compressed sensing needs, there's kind of three ingredients that you need to put into the soup. The first one is you need to take compressible signals. So you need to have some sparse transform representation. For example, the wavelet transform for brain images. You want to make incoherent measurements. So I will talk about that, but for example, randomly subsampling the Fourier domain gives you that kind of incoherence criteria. And then finally, you need to reconstruct using a sparsity enforcing nonlinear reconstruction that iteratively separates sparse signals from the artifacts. Okay? I will explain maybe through a more intuitive type of example. So here's a signal, one-dimensional, sparse in the signal domain. These are the elements of the signal. MRI spits up frequencies, and I'm just showing each frequency individually, laid upon each other, but really you measure the addition of all of these. Okay? Now, according to Nyquist, there's a rate that you need to acquire that signal in order to reconstruct, and if you do, you only need to take an inverse Fourier transform and get the signal. And we showed that before. If you do equispace subsampling, you get aliasing again. But what's a problem with this uniform subsampling is that there's inherent ambiguity. You see replicas of the signal. We know the signal is sparse, but it's a little bit unhelpful because I need to pick which one of them belongs to the signal. I just don't know. Each one of them are kind of equally likely. So it's very, very hard. What if I go for a randomizer, pseudo-random, or non-uniform type of sampling? Well, then I get aliasing, but now that aliasing is incoherent. Okay? Now what I often see is I see some of the signal elements and some are going to be buried by the incoherent aliasing. Okay? But the incoherent aliasing is, it kind of looks like random noise, but it's not really random noise. What it is the leakage of energy from these signal component that leaks into other signal components because we did the subsampling. Okay? But the thing is, once I know the signal components, I can completely and accurately compute that interference. So that leads to a very, very simple, intuitive recovery algorithm, which has some faults, but I think it's very intuitive, so that's why I explain it. So here's a simple recovery. I randomly subsampled, I reconstructed, I get this random interference. Some coefficients are going to be above that interference. They have to, because they generate it, and because they generated it, the interference has to be lower than some of the coefficients. So now I'm going to set a threshold and say, well, these coefficients have to be in the final solution, so I'm going to take them out. Took them out. Now I know what the sampling pattern was, so I can compute what the interference that these coefficients create. And this is the interference that they can create. And so what I'm going to do now, I'm going to subtract it from the original signal, lowering the interference level, and be able to recover that guy that was embedded before in that interference, and then set another threshold and recover the signal completely. Now this is an intuitive example. There's some faults to my description. For example, these are also corrupted by interference, but that is the basic idea, and they can be solved. And this idea comes also from in digital communication, like your cell phone when they communicate with the base station, operate in a very similar way. Okay, so here's a question. Let's say our signal is sparse, and we sample it directly. We sample it here. Would compressed sensing work? A, yes, most of the time. B, yes, but only if it's very, very sparse. C is unlikely to work. Or D, only with sophisticated reconstruction we can still make it work. All right, now we got a distribution. Okay, so the right answer is unlikely to work. And the reason it's unlikely to work is because we sample a sparse signal directly, and we're most likely to miss the sparse signal coefficients. Okay, so we're just not be able to capture it. And so that leads to the domains of compressed sensing. Okay, in compressed sensing there are kind of three domains. One is the signal domain. One is the sparse domain, and then the other one is the sampling domain. The sampling domain should never be sparse. It should have the signal distributed all over its space. The signal doesn't have to be sparse, but it should have a sparse representation. And these two have to be incoherent with each other. That means that some sampling over here will create random kind of noise-like artifacts in that domain. For example, if in MRI, 2D images, signal domain would be, for example, an image. K-space would be the sampling domain, where the signal is not sparse. And then those would be somewhat incoherent, although not fully incoherent, with the wavelet domain, and mostly incoherent with those fine, high-frequency information. But if we look at dynamic cardiac imaging, for example, that will be XT domain, the space and time domain will be the signal that we want to reconstruct. K-space and time will be the signal where we sample, and then XF, the temporal Fourier transform will be where the signal is sparse, and those are incoherent. Okay, so this is very important. So now, how does actually a compressed sensing reconstruction work for images? And let me show you an intuitive example, although this is an algorithm you can actually implement, and I'll show you actually a link where you can download a tutorial where you can go through. So we start with acquiring randomly subsampled variable density data. We reconstruct an image by just doing an inverse Fourier transform with zero filling. Now this is corrupted by interference. Okay, so we can kind of see through, but it's still corrupted. What we're going to do then is do some sparse denoising. We'll do a sparse transformation. You kind of see some of the coefficients. They're buried in noise. What we're going to do is we're going to try to denoise it. Now here you can plug in your favorite denoising algorithm. You can take one of these advanced dictionary learning. Oh, what did I do? Okay. You take these advanced dictionary learning type, or you can just do a wavelet transform. There's all of these you can plug in here. Okay, so we denoise some of that interference and get some estimate. We take this estimate, we compute back K-space, and we use it as what we do then is we do some sort of data consistency, either by completing the missing data, or maybe mean square error or something that will make the data more consistent with what we acquired. Then we do it again, get a better estimate, denoise it again, get a nicer estimate, compute K-space, enforce data consistency, do it again. As we get better and better reduction in our interference, and we expose those that were buried by it, and finally get a final image which will be reconstructed. And this is actual reconstruction. Now you can download the tutorial code. It's available on my personal webpage, and just go through implementation of this in MATLAB. Okay, so really theory though can take you only so far, because there's many practical considerations when you go and implement these kind of schemes in practice. For example, medical images are not truly sparse. They're only sparse in the weak sense. It's not just few coefficients, but just a few large coefficients and very small coefficients. So you have to deal with that. Noise, of course, is a problem. Sampling, pure random sampling, is in fact infeasible. But it is feasible in some situations, so you need to think where it is. And so there's a lot of things, and I'll just go through just a few of those. One thing is very important. This is not magic, okay? So noise is a limitation. But noise in the sparse domain, that's the one that counts. Okay, it's not in the image domain. The one in the sparse domain, that's the one that counts. When you subsample, that is going to reduce your SNR of the image. There's no way to get around this. The resulting image noise is not going to be wide Gaussian anymore because you're doing a nonlinear recovery. You have to take that into account if you do fitting and modeling afterwards. And the apparent SNR and sensitivity are not the same as the, apparent SNR and sensitivity are not equivalent. So you can only use this when SNR is sufficient. Okay, so here's an example. This is a reconstruction. We set a threshold, we remove. This is the remaining artifact noise. Okay, and so we can recover this guy. But if our true noise overwhelms this guy, there's just no way you will be able to recover it. Okay, and that's why noise in the sparse domain counts. If it's too noisy, then you're not be able to be sensitive. So that's the difference between SNR and sensitivity. Artifacts. When you push things to the limit, of course it's going to break, but I would say that they're usually easier to recognize, although sometimes can be subtle, but people do get used to watching them. What you see is kind of a wash contrast, loss of resolution, synthetic, artificial look, very much like compression artifacts. Guess what? This is very similar to compression, so you get kind of compression artifacts. So it's just an example of some blocky artifacts that you can get because you were using certain transformations. And this is very similar to compressing, like if you over-compress images in your digital camera, you get similar artifacts. Here's interesting trade-offs. If you can use compressed sensing to change the trade-offs. For example, if you just go for acceleration using low resolution, you lose low resolution. That's pretty obvious. But with compressed sensing, first of all, your trade-off is better. As you increase the acceleration, you can still reconstruct, but at some point it's going to break. And what you're going to see is loss of features that have low contrast because they're not sparse. But what's exciting is that if a feature is so small, but it has high contrast, you'll be able to recover it. So that's a different trade-off. How do you do incoherent sampling? Well, one way is, for example, out of 3D acquisition, you can just subsample the phasing codes. And that gives you complete 2D randomness. Other ways that people have devised, for example, is if you do 2 dimensions, you can do radial, variable density spirals, or even think of KT randomized sampling. But eventually, you need to think of how that's going to affect in the domain that you're going to do the denoising. Reconstruction speed, there's no way to avoid this. We're going to use iterative reconstruction. It's computationally intensive. Very large data set, that also where compressed sensing behaves better. So currently I would say that this is the top hurdle in penetration to the clinic. There's current solution, people try and come up with better algorithms that converge faster, they're more efficient, or just use parallel computation. But ultimately we can get now up to 1 to 3 minutes reconstruction for 3D data sets, which is pretty fast. So back to question 1. What are the key elements of compressed sensing? A, acceleration, reconstruction and speed. B, FFT, well, just read it. Oh, come on. Do it again. No. All right. I guess you can never. All right. So just to conclude in some comments, compressed sensing really does sparsity, incoherency, and nonlinear reconstruction. We use iterative denoising to LES the artifacts. That's effectively what's happening. Implementation must adapt to the application because how you actually do the random sampling and so on and so forth. Use when limited by the encoding time but not by the signal-to-noise ratio. And I would say use for larger dimensions. For example, 3D, dynamics, flow, diffusion, more dimensions. That's where signal more redundant. Personal note, take it easy, really. Acceleration does cost, and it costs in the SNR. So use carefully and responsibly. There's a lot of need to clinical validation, and I urge the vendors to give packages with implementation so people can actually try. Share your code so works can be reproduced, and our code is shared on my page. I'd like to acknowledge the people that contributed to slides, and I would summarize with a quote by John Pauly. He says back in 2007. For those of you who heard, you'll hear it again. Everything to do with compression is very contentious in medical imaging. Every time you throw bits away, somebody gets very nervous about it. And the fortunate thing about compressed sensing is that you don't collect them in the first place, and that's a much better situation. And with that, thank you very much.